Next speaker will be Mathieu Micoulaut.
Hello.
Are you with us?
Hey, привет. Hello.
Okay.
Bonjour.
Salut.
Can you hear me?
It's just a moment. I will introduce you. Mathieu Micoulaut is professor in Sorbonne University in Paris and a very big specialist in molecular dynamics of ab initio or first principle molecular dynamics. It's sufficient to say that he was the first who introduced van der Waals corrections for tellurides, and it was really a very big step forward to understand properties of telluride phase change materials. So it's up to you now.
Thank you. So, and you hear me?
Yeah.
Wonderful. Bonjour. Привет. So I would like to share some of our results that you have accumulated on selenides, on chalcogenides, and mostly on amorphous phase change materials. So these are, my group is located in the historical center of Paris, in the downtown area. That's the red dot that you can see here from our office. We see the Seine River and Notre-Dame de Paris, the cathedral. And so the results I'd like to show today have been essentially is a result of collaboration of several colleagues from Université de Montpellier, from Universidad de Guadalajara in Mexico, and Cincinnati. Also UCLA, my former student is there right now. So we have some interest in chalcogenides. So Eugène just introduced this fantastic family of alloys and materials. We are basically trying to alloy them sulfur, selenium, or tellurium with various elements of group 3, group 4, group 5 elements to design dedicated applications like in optoelectronics and phase change and data recording, of course, but also infrared fibers, optical fibers, and solid-state batteries. The interest of all these glasses or amorphous systems is, in fact, that you can almost continuously tune the composition from, let's say, 0 for pure selenium or pure tellurium with various composition, multi-composition to target a certain number of properties. For example, we have just heard about GST, germanium, antimony, tellurium, which is used in optical data storage. I should also mention that you could eventually imagine the sulfide analog of silicates, for example, sodium silicates, which is a sodium thiosilicate or even germanate, which is used in solid-state batteries, or at least they can serve as promising systems or model systems to improve the ionic conductivity. So the other typical feature is that, as I said, you can continuously tune the composition, starting from a 0 selenium or sulfur network, which has a chain, one-dimensional chain-like structure. And as you add, for example, here in the picture I'm showing here for this selenium-rich system, you are adding more and more germanium tetrahedra, and so you basically change from this one-dimensional network, you cross-link it, and you end up with something with 3-dimensional. Here's GSC2 on the right side. And what is interesting is that many different physical, chemical, mechanical properties, or even optoelectronic properties change with this composition. For example, I showed here two typical examples. It, of course, impacts the structure, and we have just seen in the previous talk how the structure is affected by composition. Here's for a family of selenides, the typical height amplitude of diffraction pattern, the first sharp diffraction peak, how it changes with network forming concentration, germanium, silicon, or phosphorus. Or another quantity in the binary GE-SE, you can see that even dynamic quantities which characterize the onset of glassiness, glass relaxation, how you can eventually detect anomalies, that is a minimum or a maximum in physical chemical properties. So maybe I'll go a bit faster on this slide because you already heard about. So the issue of phase change is based on the unique properties of those chalcogenide glasses. And you're basically switching between a crystalline state, which has a low resistivity, which is semiconducting at low temperature, with an amorphous state, which has a high resistivity. And the difference in resistivity or even in optical contrast can be up to 6 orders of magnitude, depending on the composition, on the film quality, on nucleation site formations, etc. And so this is widely used in optical disk writing and data storage. The principle is that you basically start from a crystalline system. Here you can see the material with grains and boundaries. And as you raise up the temperature, you will locally melt it. And as it cools down, it forms a glass, or at least a amorphous state, which is embedded in the crystalline matrix. Because of the difference in optical or electrical contrast, you can read it, and eventually you can rewrite on it or erase it by heating it up. In this case, the amorphous phase will recrystallize, and you have basically erased the data. So the target systems, they lie on this magic line that was mentioned before, a line connecting in the GTSB triangle, the line GTSBD2T3. I like very much to show this particular slide, which puts the whole in perspective in terms of history. You have to remember that, well, the basic idea of writing between an amorphous and a crystalline phase traces back to the work of Stan Ovshinsky, who published a paper in Physical Review Letters in 1968. So this is and I actually plotted the number of research papers on phase change plus tellurides plus non-volatile memories with a number of years. As you can notice, at the very beginning, there was not much activity on this kind of topics. Yuho Namada even called a death valley the period in the 80s when almost no research was performed on that kind of materials, till Panasonic launched the first optical disc based on phase change switching and using these telluride systems. And then, as you can see, the number of papers increased dramatically, and of course was also used to design new applications such as DVD, rewritable, or even the Blu-ray. So basically, between this now modern applications and setups and the initial PRL, there is nearly 35 years. So there is one very fascinating model which comes from Kolobov, who suggested that actually the difference in contrast arises from a difference in local geometry. That is, between the crystalline GET that you can see on this left figure, which is octahedral, and the amorphous one, there is just a simple switch from something which is octahedral to something which is a tetrahedral germanium. And so the suggestion, the main conclusion was that germanium should be tetrahedral in amorphous GST. And basically that everything relies on a transition between octahedral G in the crystal and tetrahedral G in the amorphous system. However, this typical feature was not seen in simulations. Essentially, various groups performed quenched glasses using DFT calculations, and they could show, that's the figure that you can see here, that if you look at the bond angle distribution around germanium, it looks pretty much the same as the one that you can obtain for an antimony centered bond angle distribution. And they display basically two features, a main peak at 90 degrees and a secondary peak close to 160, 180 degrees, which clearly signals that the system is octahedral, that germanium is octahedral. And actually, the main conclusion was that this umbrella flip model is probably not valid, first point. And the second point is that germanium is a dominantly defect octahedral site. So we want to probe those materials using ab initio MD. So first, maybe I should remind that on the atomic scale, you cannot use classical molecular dynamics using a force field. And this becomes already obvious if you look at a very simple GSE2 system, because if you compare the results that you would get from a classical force field, like for example, here's a Vashishta potential, which is very well known in the literature, and you compare it with results from partial percolation functions accessed from isotopic Newton diffraction, you can see that the simulation completely fails to reproduce typical homopolar peaks that appear in the GG partials and in the selenium partial, that is here in red. Furthermore, you can't deal with the charge transfer, which is typical in covalent character of the chemical bonding that you encounter in those chalcogenides. And of course, one expected is becoming even worse in semi-metallic tellurides. I should briefly mention that there may be alternative paths to ab initio simulations like machine learning, and there are very recent efforts on this kind of topics. So basically, we want to use ab initio MD. So the very difference between classical MD and ab initio MD is that you use a density functional theory. That is, you reduce the whole problem, electronic problem, to one electron density. That's typically the central work of Kohn and Sham. Of course, you have a price to pay, which is the introduction of a correlation energy and an exchange energy. But in principle, you basically solve the same kind of equations. That is, once you have got the electronic orbitals by solving the Schrödinger equations from the positions of the atoms and have computed the electronic density and then extracted the forces, you are able, using the same Verlet algorithm, to integrate the equations of motion for the ions to get velocities and ultimately positions. So in principle, in ab initio ND, you don't need force fields. It's of course a heavy computational cost because it's self-consistent, and basically it reduces the number of atoms of your system. So you're dealing basically with 100 to 500 atoms, whereas it's about 10 to the 7 in classical MD, and the simulation time is reduced to 100 picoseconds. So, but it provides very, very nice agreement with experiments. For example, in arsenic selenium glasses, here you have the percolation function, which can be very nicely compared in blue with previous experiments in yellow, or the circles from Jean and Salmon or from Fabian and others. And you can also notice that it describes much better the structure as compared to a classical force field, like the one you see in red, which is from Mauro and Varshneya. It also agrees with partial correlations that you access from anomalous X-ray scattering. Here I show on the right side, on the top, a comparison solid line with respect to the circles which arise from experiments. The other interesting contribution on this system is that you can eventually calculate the infrared absorbance spectra. Here's an example for AS2 SE3, where you can see that at ambient, you reproduce the main features of the experimental spectra, which you see as the red broken line. And furthermore, I should mention that this infrared spectra is calculated from the polarization autocorrelation function Fourier transformed. But furthermore, if you look at isolated clusters, which might be present in the system, like tetrahedral arsenic or quasi-tetrahedral arsenic, you can see that they have a typical frequency, which is close to 400 wave numbers. And that is also found as a bump in this calculated spectra. So there might be some features related with defect coordinations in these systems. And as you can see, that amplitude grows with increasing temperature. And this might, in fact, be compatible with the population of arsenic 4, which increases as you increase the temperature. And around 1,000 degrees, that fraction is about 40% for arsenic 4. It's, of course, a minority population at room temperature in the glass, which is less than 10%. So let us switch now to phase change materials. Phase change materials, we have been playing with systems with about 200, 300 atoms. Here are some details for those who have some interest. So it's a functional exchange correlation, which is PBE with a GGA approximation. The cutoff is about 20 Rydberg, and to integrate the equation of motion, we use basically a time step, which is about 0.12 or 0.2 up to 0.36 femtoseconds. So we cool the system by steps. different systems have been investigated. I will target today on essentially phase change materials. So here's the first figure that I would like to show, which is an uncareful simulation of GST in the liquid, 800 Kelvin, compared to neutron diffraction results. And as you can notice, the agreement is very poor. That's the first point. And the second point is that there is obviously a bond mismatch between the first peak, which is essentially arises from germanium tellurium bond distances. And as you can see, it's shifted to the right, the simulation. So clearly overestimated 2.78 for the theory, whereas it's 2.61 for the experiments. And so this tells us that, well, first something is wrong. And second, then we realize that if you include dispersion forces, that is a correction which is due to Grimme. So a dispersion force behaves as 1 over R/6, or the distance between the atoms or the ions. In this case, you can correctly very nicely the structure models that you obtain, and now they can really compare very well with experimental data. I should remind that these coefficients that you can see, Cij, including the damping function, then can be either obtained from tabulated data, which correspond to gas phases, or they can be directly calculated, for example, from maximum localized Wannier functions. So the results from amorphous GET, here is a PB, a first result, which doesn't use those Grimme corrections, those dispersion corrections. And you see that the agreement is not that good. It's also true for the alternative exchange correlation functional. And as you use that green curve and you switch on the van der Waals or the dispersion correction, you see that everything now maps very, very well on the experimental red curve. So we have found for a variety of systems in the amorphous phase, but also in the liquid phase, that the inclusion of those dispersion corrections was correcting very nicely the structure functions in reciprocal in terms of structure functions, structure factor, or for the percorrelation function. The comparison between theory calculated structures and measured ones. For example, here you see different ternaries in the GST liquid, where the red curve, which is a calculated one, compares very well with the black one, which is the experiment from neutron diffraction. These are results from other groups, the blue curves, so I won't comment on that. So, and here's another example, again in the liquid, but on binary GETE, where now I have represented the red curve, which is the MD simulation. The black curve is the experiment performed in Grenoble. And the green curve is exactly the same simulation, but without the Grimme correction. And now you clearly see the shift to the right to larger distances of these poor or spurious simulations with respect to the curve obtained on which are in red. So clearly there will be an effect on the coordination number, because the integration of those peaks gives you the coordination number, and of course an effect on the local topology. So in fact, if we look into details, into partials here, let us take the G20T80 in the liquid. We see that this structure is dominated by a main peak which arises from GETE correlations. There is a minor contribution which is arises from TET correlations, and then a very small contribution that you see the solid line, blue solid line here, which arises from GEG correlations. So we realize that the bond, what is called the bond distance problem in those tellurides, is resolved with the Grimme correction. Here I provide you numbers for this main peak and of the GET correlation. We see that with the Grimme, the distance is very close to the experimental one, whereas without the Grimme correction, it's much highly, substantially overestimated. And so the corresponding coordination numbers in those typical systems, of course, with the Grimme correction, will be reduced with respect to their counterparts from the red lines when we don't take into account those corrections. So now we want to estimate tetrahedra. I have to apologize, this figure is a bit busy, but we'll spend some time on it if you permit me. So we would like to evaluate the fraction of tetrahedra in those systems. First, we have to remember that a tetrahedra is defined by 6 rigid angles that we call also constraints. Actually, there are only 5 which are independent, but if you find 6 rigid angles around a germanium atom, then we are sure that we're dealing with a tetrahedra. So from the trajectories that we obtain, we don't look at angles, but we look instead at angular excursions. And if we are able to identify around a central germanium atom 6 small angular excursions around that atom, then we're sure that we have a tetrahedra. So we plot on the first panel, we plot as a function of the angle number, the variance of those angles, of those local angular distributions. And we can see that for the blue curve, for the blue bars, we detect 1, 2, 3, 4, 5, 6 angles which have a low standard deviation, which means they have a low angular excursions, and this is a signature of tetrahedra. The other population, as you can see, has a much larger angular excursion for select angles. We can see the angle number 3 or the number 7, number 10, and we have basically only 3 small standard deviations for those germanium atoms. So now we have identified those atoms, we are able to calculate their corresponding average angle. And we can nicely see that those blue bars give rise to angles which are about the tetrahedral angle, indeed, whereas the angles, the germanium atoms which have only 3 rigid angles, so the angle 1, 2, and 6, give rise to a mean average angle, an average angle which is about 98 degrees, and you find them here 1, 2, and 3. So we are able to split the population into G having 6 angular constraints, which are tetrahedra, and a residue, which has only 3 constraints. And now we can evaluate those numbers, and we detect that in GT, we have more than 50% of tetrahedra and about 90% in for the corresponding silicon tellurium. Now we can also plot the corresponding bond angle distribution, and we find for the same system that you have a first distribution which is indeed centered at 109 degrees, tetrahedral angle, which is very, very close to the one which you would calculate for the corresponding selenide. And then you have a residue, which is the one centered at 98 degrees. Furthermore, I should mention that with the Grimm correction, you get actually a fraction of tetrahedra, which is much larger than a simulation without the Grimm correction. In fact, without the Grimm correction, you will find only about 23% of tetrahedra. And this is actually linked with the bond distance problem, because the smaller the distance, the larger fraction of tetrahedra you will find. This is a feature that is very well known in polymorphism of silica, for example, where the bond length increases with the fraction of the octahedral population. So we can play the same kind of games with ternary for various systems extracting the fraction of tetrahedra. Here again, I plot you for the same system what would be the distribution of both population, bond angle distribution for both population with the Grimm correction or without, where obviously without, you see that the contribution from octahedral or defect octahedral germanium is enhanced. And so we can go through effects of composition. Here, for example, in the binary GET, we see that the fraction of tetrahedra evolves with composition. It can eventually be compared with an estimate from Nussbauer spectroscopy, which has a typical signal if you have a tetrahedral site and doing tin substituted Nussbauer. I should also signal that now if we do this on the phase change materials from GT or GST, we find indeed that GT and GST are dominated by a tetrahedral geometry. And again, without, if you do the same simulation without Grimme, then in this case, this fraction is substantially reduced. So this is actually also in line with a very recent Maxwell spectroscopy on GST that has revealed that the tint substitution actually reveals 100% tetrahedral sites. And there is obviously an effect of compositions on this tetrahedral fraction. We see it here in the binary GET, but we will see it also in other systems. So we can also look at the corresponding pair correlation functions. Once we have now identified which atoms belong to a tetrahedral site and which GE atoms belong to a residue germanium population. So here's the pair correlation for the tetrahedral. So we see that we have something which is very, very close to what we would expect for selenides or for sulfides. That is a very well separated peak between the first peak and the second peak of neighbors. Here we have indeed 4 neighbor distribution functions which are very well separated from the 5th, 6th, etc. Neighbor function which contribute to the second shell of neighbors. This is actually a variance with the residual G, which, as you can see, first has a main peak which is shifted to larger distances indeed, and which has a very complex population, which signals us that you have indeed a defect octahedral site. We have coordination defects, 3-, 4-, and 5-fold germanium, that some of them extend to the second shell because you have long and short bonds in this kind of geometries. So we have some consequence for electronic properties, and I show you just one single figure telling you that actually the tetrahedral germanium, we have identified those atoms, and now we're able to say that they are tetrahedral germanium contribute essentially to the conduction to the valence band edge, as you can see here. TGE is the S band contribution of tetrahedral germanium. TGE is the P band contribution of tetrahedral germanium. You can see that both have a dominant contribution around the Fermi level and the gap, and the residue has a contribution that is much smaller. So furthermore, we also see that these contributions represent an increased defect state in the gap. In blue, you can see the calculated crystalline gap, and here the solid line is the one arising from tetrahedral S or P band germanium, tetrahedral germanium. This is the residual germanium, which is much closer to the Fermi, to the calculation for the crystalline electronic density of states. However, if we pick up those contributions and we look at inverse participation ratios, we notice that these contributions are much more localized. That is, that the inverse participation ratio is smaller with respect to the one arising from the residue. So this signals us that they're in fact much more localized and probably don't contribute to ionic, not ionic, but to conduction or to contrast. So the last issue I would like to address is the issue of finding a flexible to rigid transition. We know that in lighter chalcogenides, selenides, and sulfides, there's a very peculiar transition which goes on as you increase the crystalline density of the system. There's here on the left side, you can see a system which is selenium or sulfur rich, which has only a very few number of crystallings, and as you increase the network conductivity, you indeed end up with this tri-dimensional network. But you also increase the number of what is called mechanical constraints or topological constraints. And as you go through to this increase, you will hit a rigidity transition, which is satisfied as as the number of mechanical constraints matches 3, which is the number of degrees of freedom per atom in 3 dimensions, and which corresponds to a very well-known criterion in trusses or bridges, which is known as the Maxwell criterion or Maxwell isostatic criterion. In those networks, it happens at a mean coordination number of 2.4, the average coordination number. So it's easy to see that if you alloy 2-fold selenium with a 4-fold germanium, at some point you will reach that particular transition. So it's basically a flexible system where the system, it has local deformation modes to stressed rigid transition, a system where you have frustration because not all bond lengths can have the same length, and the system is fully rigid because there are no deformation modes. Interestingly, you find anomalies in those as you go through the transition, which manifests by minima, by various extrema, or a certain number of anomalies. So the question is, does this transition exist in tellurides? So we looked up those different systems now in the GSBTE system, not only 2 to 5 here, but only supplementary compositions, going through a possible flexible to rigid transition. I should remind that in selenides, for those tanneries, a transition is expected at 13%, which would lie around here between the second and the third red dot. So we first validated the structure models from our ab initio simulations. Here's an example, a comparison with X-ray or neutron diffraction results. And then we did an application of constraint counting algorithm to get the fraction of constraints. We have just seen how we calculate angular constraints from the tetrahedral fraction. So the result is shown here. We first see that again, in GST 2 to 5, we have two populations, a population of tetrahedral GE, we just found the fraction in the previous slides, and a defect germanium, which has essentially the same features as the one you are expecting for antimony, which is dominantly fourfold with 2 vacancies. We find a clear evolution with composition of those typical geometries. We find for the twofold tellurium a continuous decrease from 90% down to 60% for the 2 to 5. We find a decrease of the tetrahedral fraction for germanium from about 80 to 55. That's the fraction we found for GST 2 to 5 previously. And this can be eventually compared with the binary GET, where we could find a minimum in this tetrahedral fraction for germanium. So now if we focus on the number of constraints as a function of concentration in this GST with changing G and SB content, we find a locus of the rigidity transition that is as NC equals 3 at a composition which is about 8.5 GeSB. And that composition is smaller than the one you obtain for the corresponding or isochemical selenide, which is found about 13%. If we compare now those numbers with, let's say, archetypal selenides, which have been investigated in the context of rigidity transitions, we see that the shift of this isostatic criterion, which is at 2.4 in these binaries, typical binaries, is shifted to higher coordination numbers. And so this arises from the fact that for a mixed effect arising both from an increased coordination number of the species, but also reduced fraction of topological constraints, because some of those constraints are broken. We have also a reduced fraction of tetrahedra in the systems as compared to GESE or GES, where the fraction of tetrahedra of germanium tetrahedra is 100%. So having identified this, let's say, magic composition in this ternary, we have been wondering if we are able to produce glasses, because one of the interesting point of those isostatic stability criterion is usually you form glasses more easily around that composition. And so one expects to produce glasses in this GST triangle, which is known to have a very, very high crystallization tendency. And so we did this. This is a work in collaboration with colleagues from Montpellier. And so we generated from co-evaporation techniques a certain number of samples along that line. Only a select numbers were exhibiting glass transition temperature, that's the filled boxes. But clearly we can see that we can form amorphous systems. We also extend now the glass forming range of this ternary, which is the blue zone which is known to a very, very small glass forming range. We extend it now to this particular join. And furthermore, if we analyze the glass transition temperature with respect, for example, the mean coordination number, which is a nice way to put different systems on the same plot, we realize that's the red symbols, that those measured glass transition temperatures have a very, very different behavior with respect to archetypal selenides, where basically the increase of TG is deeply linked with the increase in conductivity. And so basically here the TG seems to be much closer to an isochemical, which is GIST. But globally, there is a very small variation of the glass transition temperature with coordination number change. And I should also mention that those glasses are highly unstable because the thermal stability, which is basically the difference between the recrystallization temperature and the glass transition temperature, is very small, about 10 to 20 degrees Kelvin. So in summary, I have shown you that those ab initio studies permit to study really in detail atomic scale properties. We have just seen in the slide, in the talk before, the work of Eugène and his group showing how various systems, gallium tellurides, germanium tellurides, can be investigated from first principle or ab initio simulations. Here I've shown you some other examples. I have shown you how the dispersion corrections, the van der Waals corrections, is crucial if you want to describe correctly telluride and phase change materials. And furthermore, then I have tried to convince you that if you calculate the fraction of tetrahedra in a very rigorous way, that is not relying on angles, but on angular excursions, in this case, we realize that the fraction of tetrahedra is very large in those phase change materials. So this contradicts previous findings from ab initio simulations, but which were working without the Grimme corrections, so which basically were exhibiting this bond distance problem, this overestimation of GET bond distances. And finally, having in hand all these trajectories and tools, we have been applying constraint counting algorithm to identify a possible flexible to rigid transition in this GST system. And so this might open also an avenue for exploring the glass forming tendency of this GST system, starting from this isostatic composition that we have identified. So, and I thank you very much for your attention. Merci.
Thank you, Mathieu. We have time for one short question.
Victor Sokolov, Institute on Photonic Technologies. My question concerns the special resolution which can be achieved in thin films made of phase change materials. Since everybody needs the highest degree of integration, for example, in memory devices, what is the special resolution?
The special resolution of those phase change materials?
Yes. Between areas with crystalline phase or amorphous phase?
Well, I'm not the expert in technology, but if I remember well, it's about tens to hundreds nanometers. The size of the spots that you could eventually write to store either the amorphous or the crystalline phase.
Thank you.
Thank you, Mathieu.
Thank you.